homework 1 in 2 classes of this week. Yeah. So then at the weekend, I will post our midterm test questions to give you 4 days to complete. All right. Yeah. Friday, Saturday, Sunday, and Monday. These 4 days. So you work on 25 questions. Yeah. These 25 questions based on our old questions, not brand new questions. So based on all those questions you have seen in our 3 quizzes plus 1 homework assignment. Okay, so that's our plan. Yeah. All right, so let's start. All right, so from quiz 2 first. 10 questions, quiz 2, then 10 questions in quiz 3, then homework questions. Yeah. All right, so today I'd like to cover 2 homework, relatively hard 2 homework questions. Yeah, the remaining I can leave to Wednesday, not Wednesday, Thursday. Yeah, today Tuesday. So our next class on Thursday. Yeah, remaining questions on Thursday. Yeah. All right, so let's start. Oh, just a minute. Sorry, I need to get my remote control. Yeah, I forgot to connect remote control. All right, sorry. Yeah. Okay. Yeah. All right. Yeah. Some questions pretty easy, so I can go pretty fast. Yeah. But for those relatively hard questions, then I spend a little more time. Yeah. But I like to follow the order 1, 2, 3, the natural order. All right. Okay. Yeah. So we can go now. The first question here about basic operation concept. Yeah. For the basic operation, basically you look at, so which operation? So usually we may use several, so not just one. So which one is the most commonly used? Okay, yeah. Because some of the operations, although each one may take a lot of time, but we do not use it frequently. Okay, yeah. But for some operations, we frequently need to use it. So we pick that one. Yeah. So in class, we use, because in class or in our textbook, so we use that, inner loop. Inner loop. Yeah, so that is the one in the inner loop. Yeah. Because this concept, yeah, the reason, yeah, this is from the textbook. Okay. Yeah, because this one, just imagine typical situation. So this is a typical situation. Yeah. Usually you have nested for loops. For loop structure. So outer for, then inner for. Okay, yeah. For example, operation 1 appears in outer for, but operation 2 appear in inner for, so you should select this one. Okay, so this is the picture to be based, for this textbook suggestion. Yeah. And here in our polynomial evaluation, multiplication is the most frequently used. Yeah. Because, so if you look at the polynomial structure, a0 plus a1x plus a and here, so you can see, yeah, you use outer for loop, and you go through all the terms. And inner, here, let me just write a typical representative term. So this is the inner, okay? In this inner for loop, yeah, that is the inner for loop, all right? Yeah. And the inner for loop, you can see you need to do multiplication in multiplication here. Okay, yeah. So that is the basic operation concept. Yeah. All right. The second question, bubble sort. Which of following types of operation is the basic operation? Yeah. In bubble sort, we use these two, but comparison is the basic, not swap. Okay. Be careful, not this one. The reason is very simple. The reason swap operation occurs only when an adjacent inversion is detected. Yeah. Recall the bubble sort, right? You only look at two adjacent elements for inversion. If there is an inversion, you swap those two elements. Otherwise, move to the next adjacent pair of elements. That's the main property of the bubble sort. Okay? If you do not have any inversion, now think about an ordered array. Yeah. So you use an ordered array as example. An ordered array. In this case, there is no inversion. No inversion means no swap. But you need to do comparisons, right? So that means comparison operation is more fundamental. All right, yeah, so we choose it as the basic operation. Okay, all right, yeah, so these two questions check your understanding on the basic operation concept. Yeah. Number 3, L'Hopital's rule. So the question we can always apply, the answer is false. Yeah, because there is a important condition you need to check it before you apply the L'Hopital's rule. So I hope you know, yeah, because we take derivative of numerator, denominator, and the ratio of two derivatives after we take the limit, it should equal to the ratio of the original functions for the limit. Yeah, but that condition is important. We can only apply it on indeterminate indeterminate form. Yeah. So usually infinity over infinity, yeah, 0 over 0, yeah, in calculus, if you recall, 1 to the 0th, right? Yeah, and how about that? Yeah, 1 to the 0th, yeah, yeah, and probably is a few more, right? Yeah, okay, yeah. But for our class, we consider the first one. Yeah. Otherwise, if it's not indeterminate form, so usually when you see a typical case, a constant, and over infinity. So this is not an indeterminate form. Okay, because we know this 0, its limit goes to 0. You do not need to use the L'Hopital's rule in this situation. Yeah. Yeah. So then you can apply. Yeah. All right. So that's the point, the main point here. Yeah. What is the growth function of the running time efficiency function for the bubble sort? The bubble sort for the all 3 cases. Yeah. So you need to be familiar with the bubbles. All 3 cases, yeah, the running time efficiency function. So we know the best case, the worst case, and the average case. And the growth function the same. Okay, so that is this square case. Yeah, so that's simple. Yeah. All right. Yeah, but if because some students look at the textbook, and in the textbook there is a modified version of bubble sort. A more modified version from the textbook. So what's that? It's a just simple modification. So that idea is very simple. If no inversion is detected in one round, because you need to do scanning in many rounds. Okay, the scanning like that. So that's the bubble sort, the scanning. Yeah, so that's the oh, sorry, just the opposite. All right, yeah, yeah. The scanning is like this. The first time the whole array. Second time, just skip the last element. Yeah, scanning like this. Yeah, not, yeah. All right, scanning like that. Yeah. All right, yeah, then stop. Okay, yeah. The scanning way, like that. Okay. So any round, so if, yeah, because you need to use a counter variable. Each round, you need to use a counter variable to count the number of inversions. If the inversion, that number equals 0, any round, if no inversion detected in one round, stop. Okay, so you do not need to complete the remaining scanning. Stop immediately. Okay, yeah, because if at any place, any intermediate level scanning, no inversion, that means there is no inversion anymore. Okay, so you already get the array sorted. Why you need to do the remaining unnecessary scanning, right? So you can stop immediately. So that's the improvement. If you do it that way, that could be a little better. Okay, that could be a little better. Yeah, but still, n squared is the answer. Okay, yeah, yeah. All right, so that's the bubble sort. Yeah. Question number 5. Yeah. If a given array does not contain any adjacent inversion. Yeah. I hope you know the adjacent. Yeah. Because usually when we define inversion, we consider the general pair. Yeah. Yeah. So for the adjacent, I and I plus 1. Yeah. Special inversion. Yeah. All right. So here does not contain any adjacent inversion. Then all the elements in this array must be in place. True. Yeah. Because if there is no adjacent inversion, that means no inversion. No adjacent inversion, yeah. So that means every time you select two adjacent elements, the second one is always greater or equal to the first one. With this property, you can see the whole array is ordered. If it's ordered, then all elements are in place. That's simple. Okay? Yeah. All right. The reason, yeah, so there is a reason. Yeah. Okay. Reason by the property, you know, by the transitivity property. What kind of transitivity property? A greater than B, B greater than C, it implies A greater than C. Okay, that transitive property. Okay, so the adjacent, inversion, or in order property between two adjacent elements, that property can be transitive to the whole array. That's the main reason. So, transitivity property for that in order property. Yeah, in order property for two adjacent elements. That property is transitive to the whole array. Okay, so that's the idea. Yeah, that's the the basic reason for this whole statement. Yeah. All right. Number 6. Yeah. So here, first, the whole array is unordered. Okay. Yeah. So that means that tells us one fact: the number of inversions should be greater than 0. Cannot be 0. Otherwise, it is ordered. So your answer should be greater or equal to 1. Okay? Yeah. The minimum possible should be 1. But the question is, you need to ask the question here: can 1 achievable? Right? Yeah. Can you find a special case for which there is only 1 inversion? If you can, then your answer is 1. Otherwise, so if it's impossible, if you find some good reason to see it is not achievable, then you have to consider answer at least 2. And so on. Yeah. Here you can see, find a good example is very important. Here, so let me give you good, simple example. Okay. Yeah. Not too complicated. Yeah. So it's a good, simple example. Okay. So what's that? All right. So when we start, we consider start from an ordered array. How about that? An ordered array. Yeah, we know it's unordered, right? We know the main condition here, unordered. But yeah, how about here? But we can still assume when we start, we have an ordered array. Yeah. How about that? Okay. Yeah. But we need to make it unordered, right? Can we? So the next step, make it unordered. How to do it? swap last two elements. Swap. Just swap the last two elements. Okay? Yeah. If you do that, is the number of invert equal to 1? Because only the last pair of elements form an inversion. The remaining still in order, right? Yeah. If you do not look at the last pair, the remaining pairs all in order, right? Look at that. Yeah. Only take the last of the adjacent pair. Yeah. It does not affect the remaining pairs, right? You do one swap operation. So you get one inversion. That means achievable. That one number is achievable. Okay, so your answer is 1. So you can see when you answer a question like this, some students just by guess. Okay, so although they also do some analysis, but they may not do the complete logical reasoning, like the one here. Yeah, so they just do some basic analysis, then by their intuition. Yeah. So here, to answer this question correctly, if you follow the way we are doing here, using a good example to show the answer 1 is really achievable, then that's the good process for your answer. Okay, yeah. But some students, so they feel finding a good example is not easy. Yeah, I agree. Yeah, so finding good example not easy. Yeah, so you really need to have some good understanding. Yeah, so you can create the right example. Yeah. Later on, we will have many places we need to construct suitable examples. Yeah. Number 7. When you solve the element uniqueness problem, does there exist an algorithm whose growth function has lower order of growth than n squared? Yeah. Remember in class, we have two methods. Method 1, all right, method 1, n squared. Yeah, the growth function n squared. Yeah. Method 2, yeah. So we do sorting first. Sorting plus. Okay? Yeah. So then n log n. Yeah. And this is better than n squared. Yeah. So, oh, sorry. Yeah. When exists, answer is yes. Okay? Yeah. But sometimes, people may ask, is it possible to do better than this one? Better than that? Okay? Yeah. It is possible. Yeah, it is possible. Yeah, but with the knowledge we have learned so far, we cannot do that. Yeah? With the knowledge we have learned so far, we cannot. But later, when we learned another special algorithm, yeah, some of you may know that Hessian, yeah, algorithm, then we can do better. Yeah, we can do in big theta of n. Yeah. Yeah. Because when we construct a hash table, we need this much cost. And when we construct hash table, we can detect if an element is unique or not. Yeah. Yeah, because when you put in the hash table, if it's not unique, you will get a conflict. You will detect a conflict immediately. So you stop. Okay? When you detect a conflict, yeah. So when a conflict occur, so you get a duplicate element detected. Okay, so that's simple. Yeah. Yeah. Yeah, but we need to learn that algorithm first. Yeah. All right. This one, how many inversions you can find? I give you a very small array. Okay, yeah. So when we consider, and in my hint, I show you how to do the counting. Is it inversion? Yes. Yeah. Inversion? Yes. Okay. Inversion? Yes. Okay. Yeah. Then inversion? No. All right. In order, that pair. Inversion? Yes. Okay. The last one, inversion? Yes. Okay. So you count the number of checks, 5. So the answer is 5. Okay. Yeah. Counting in this way. Yeah. So you do not miss any pair, but at the same time, do not repeat any pair. Yeah. Some students could, repeat, yeah, some pair, yeah, because you consider 2 full ones, then consider, another time, yeah. Yeah, but actually, if you do this case, because if one is inversion, the next one is, yeah. But when they consider this case, they actually look at this the second time. Yeah. Then you do not count it right. Yeah. So the second time, you cannot count it another time. Okay. Yeah. All right. Number 9. When we solve the string matching problem, suppose that there are n characters for the text, n characters for the pattern. Yeah, first, you need to be familiar with the string matching problem and the terminology we used, yeah, and the representation we used there, yeah. Then, so you can understand, yeah. So the question here we need to count the number of m strings, yeah, and the formula is given in our notes, so you can find it easily, yeah. But there is one simple way you can find the answer quickly. So that is, we use a special example when n equals to m. In this case, we know the number of m substring is 1. Because that string and the pattern, same length, so you can only have one substring matching the given pattern. Yeah, so the answer is 1. But if you check the three options here, the first one give you negative, the second one give you 0, and the third one give you 1. So you can choose. The third one is correct. Okay, yeah. So use a special example to find the answer. Yeah. All right. So in the notes, when we guess the formula first. We guess the formula. By intuition, the first time we guess m minus m by intuition. But our intuition may not be accurate. Okay, so then we fix it. The problem, yeah, using that example, so we can fix it. Okay, yeah. So the answer n minus m plus 1. After we fix it, we get the correct answer. So the answer is this. All right, the last question. An efficient atom does not have to perform well, right? Yeah. For relatively small problem size. Correct. Okay. Yeah. So the reason in one video I explained that. Yeah. The reason. Yeah. Because when for the relative small problem size, the overhead part distorts the growth function. Okay? Yeah. Yeah. But after that, you increase the problem size, the overhead part basically keeps the same. Yeah. So you do not increase the overhead part. Yeah. So then your growth function becomes bigger and bigger. That distortion becomes smaller and smaller. Okay? Yeah. So when you grow the problem sizes, the distortion part becomes smaller and smaller. And finally, you can ignore it. Okay? Yeah. Very, very small, then you can ignore it. So then you can do fair comparisons. Yeah. And for relatively small size, because the distortion too big, the result is no fair comparison. All right? Yeah. Okay? Yeah. So that's the reason we want to bypass the relatively small problem size. So, to remove the effect from the distortion part. Yeah. All right. Yeah. Okay, so that is the 10 questions from quiz number 2. Yeah. All right. Before we move to quiz number 3, I like to talk about 2 relatively hard questions in homework 1 first. Yeah. Yeah. So then we we go to quiz number 2. Yeah. All right. Here, let me just jump to our part 3. Okay. Yeah. All right. Yeah. Last 2 slides. So I like to talk about those 2 relatively hard questions first. All right. First, this question. Yeah. This question, if you do not get the insight, then it is very hard. Yeah. So you need to observe the insight from your analysis. In my hint video, so I try to point out the right direction to go, but still many students couldn't get it. Yeah. Yeah, because I cannot tell you the too much information, right? If you give you too much information, so you can get the answer easily. Yeah. So that's not very good. Yeah. I like you to solve the problem. Okay. Not I give you the answer. Yeah. So that's not good. Yeah. Yeah. But in the hint, we connect to another important or related problem. So we connect to this question, finding the minimum. That question. Connect to in this way, yeah, finding the minimum. Okay, so we rewrite that question. So we rewrite that question as, all right, so given an n element array, find here we can use yeah, because for this function we use an element that is among the top one. Okay, all right. So we rewrite it that way because this version can be generalized to top k. The k number, we can change it. Okay, yeah. So this version can easily be generated to the k version. Yeah. And for this question, k equals 8. So it's just another special case, top 8. Top 8, top 1, here you can see the similarity. Okay, yeah, all right. And we have a lot of experience on the top 1 case. Yeah. So in this, our experience, okay, find one element that beats n minus 1 elements. Yeah. That straightforward. Beats. So what do you mean beats, right? Yeah. So people may ask this question: what do you mean beats? Yeah. By comparisons. Okay. By comparisons. Yeah. Then you can define the winner and the loser, right? Yeah. The comparison. Winner, loser. You can define it, yeah, based on, because if you want to find the minimum, then the smaller one becomes the winner, right? Yeah. So here, yeah, let me use more space here. Yeah. In one comparison, how do we define winner and the loser for one comparison? Okay. Winner, loser. Okay, we define here. Okay. All right. Finding the minimum, the smaller the better, right? Yeah, here. Yeah. Against your intuition, your intention, usually the larger the better. Yeah, but our goal is minimum, right? The minimum, so the smaller one is the winner. The greater one becomes loser. Yeah. But for max, then the larger one is the winner. The smaller one becomes the loser. Okay? Yeah. Here, we need this definition. Okay? The larger one is the winner. Yeah. All right. So with this understanding, now for the current question, yeah, this question. Okay? Yeah. On this question, yeah, the goal among top 8. Okay? Top 8. So the logic is like this. Find one element that beats. Okay? And minus 7, sorry, n minus n minus 8, right? Yes, not 7. Yeah, we should be careful here, okay? In counting n minus 8 elements. Okay? Yeah. Find one element that beats n minus 8 elements. Okay? Yeah. That's the goal. By analogy from our old experience, this is our current goal. Okay? Yeah. The next question is how to do that. How to make that happen. Okay? Yeah. This last step. Yeah. So I feel many students just couldn't get that last step because the hint, this information here already given in hint. In our hint video, we already have information to this point. Yeah. But we don't have this how-to step. So you need to make this how-to step. to complete the whole solution. So to get that how-to step, the last thing you need to do, if I give you here, that's so easy. But if I ask you to find it, that may not be that easy. Yeah. So that's what we mean, the insight. The insight, if someone points that out in front of you, you feel very easy. But before anyone pointed it out, you feel very hard. So that's the typical experience we have from finding some insight. Yeah. All right, so how to find any subarray with n-7 elements. How about that? Subarray with n-7 elements. Okay, this is the insight. Yeah. In this subarray, find its max. Find its max with n-8 comparisons. Yeah. And you know, because with these n-3 comparisons, we can do the same thing as in our goal, right? Yeah, because with these many comparisons, we beat these many elements. The max of the subarray beats these many elements. Yeah. So the answer is m-8, but the m is this 247 minus 8. That's the answer here. Okay? Yeah. That's the solution. Very easy, right? Yeah. But you need to do the analysis with the background knowledge we have learned here, like this. Okay, to find a solution. Yeah. All right. Next. This question in my hand, actually, I give a lot of information. Yeah. But still, like the previous question, you need to make the last step. Yeah. So you are very close to your destination, but you need to make that critical step. The last step is critical. Yeah. But you need to pay some effort. Yeah. All right. So here we have 6 elements. So the information we have, x1 is not equal to the minimum. That implies, because the minimum probably, that implies the main element is less than x1. x6 not equal to the max. So that means x6 less than max. That's the given information, very important. We need to take advantage of the important information. Yeah. Otherwise, you cannot save one So the goal, save one comparison. The goal. One comparison. Yeah. Because that's the from 3 to 2. Yeah. Without the given information, we have a 3 comparison solution. Okay. Yeah, 3 comparison. So you need to have that background. 3. So why 3? Yeah. Some of you may know why 3 comparisons. Without, okay? Without that condition, okay? Yeah, because some students, they do not have this background, okay? Yeah, then that will affect their understanding, okay? Yeah. So why? So I give you the answer. Yeah, the reason, yeah. Pick any 3 elements. Okay, all right. Say x1, x2, x3. Then solve them with 3 comparisons. With 3 comparisons, you can get them sorted. Yeah. So let's assume, the example case, x1 less than x2 less than x3. You get them sorted. Then the one in the middle, that's the solution, right? Not the maximum, not the minimum. Yeah, because so we need to find that neither the maximum nor the minimum. Okay, all right, but that's the without given information. Here we add the given information. We want to reduce the number of comparison from 3 to 2. Yeah. So now you understand the background of this question. How to reduce, yeah. So you have to use the given information as much as possible. Otherwise, you waste the valuable known information. Yeah, right. So you pick x2. All right, yeah, pick x2 to get it started. Okay. The first comparison, compare x1 and x2. Okay, all right. So you have 2 cases. Case 1, x1 greater than x2. Case 2, x1 less than x2. Okay, all right. Which one is easier? So you work on the case that is easier. You always work on the case that is easier. All right. So this one is easier. Why? Because now you connect to the given information. You have main less than x1 less than x2. That means x1 is the solution, right? It's a solution. because the solution is not unique. We only need to find one solution. Okay, not unique. Yeah, it's a solution. All right. Then the harder case, x1 less than x2. Yeah, because in this situation, we cannot find a solution. Yeah, x2. Yeah. So we need another comparison, second comparison. The second comparison, compare still x2, because we already have a lot of information for x2, compare x2 and x6. Yeah, all right. Then two cases, x2 less than x6, x2 greater than x6. Okay, look at which one is easier. Okay, so we first for the consider easier case. This is easier. Easier. Yeah. All right. Okay. Yeah. Why? Because if you connect to the known information, you will get. Oh, sorry, not that. Yeah, sorry. Yeah, let me just modify a little bit. All right. Yeah. 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 Okay, correct. All right. Yeah. All right. So because for this one, we will get x2 less than x6 less than max. That tells us solution, right? A solution. Okay, a solution. Okay, then the last case we need to consider x2 greater than x6. Yeah, look at that. Look, combine this condition, combine that condition, shaded information, these two pieces of information. Let us combine them. Combine the shaded pieces okay, these two pieces information together. All right, so what do you get? You get you get x6 less than x2 x2 here less than x1, right? Does it tell you that x2 is a solution? Right? Yeah. So then you cover all the possibilities. Yeah. Here, with two comparisons, you use those two precious comparisons. You cover all the possibilities, no missing case. Yeah. Every case is considered in this organized way. Here, you organize the known information in this way. Here, my explanation, a little messy, but if you follow, so if you can use a larger scratch paper, you can write the idea clearly, okay? Here I just write, with a limited amount of space, not quite well here, All right. Okay, so we run out of time. Yeah, let's stop right here. Yeah.